Hey folks, this is Becky, and in this video we are going to learn about or think about how reactions occur. In other words, we're going to talk about something called collision theory. Okay, so our goals of the video are to be able to describe the conditions that lead to a chemical reaction and to be able to diagram energy changes over the course of a chemical reaction for a specific reaction. Okay, so let's think about, I have a reaction where I have A2 reacting with B2 and making 2AB. So if I were to draw a particle level diagram for this, let's start there. Always like to start with a particle level diagram where I have A2, and I'm going to say A2 is my big red circles, and B2 in my case I'm just going to use blue circles, and then I'm going to make two of these AB molecules. Okay, so let's think about what's actually happening here as I do this reaction, right? Anytime I do a chemical reaction, we know that we are making bonds and breaking bonds, right? So in this case, the bonds that I'm breaking, I have to break an AA bond, and I have to break a BB bond. And then I'm making an AB bond and an AB bond. So I'm making two bonds that are A to B. So what has to happen in order for this to occur, right? In order for this bond breaking and bond making process to happen, something has to happen. Like there has to be something that occurs between that A2 and that B2 molecule. And so what happens is something called collision theory. Basically, those molecules, A2 and B2, have to run into each other. They have to collide. Think about hitting a baseball, like trying to hit a home run, right? The first thing that happens is the ball has to make contact with the bat, right? You have to hit the ball. You have to kick the soccer ball, physically make contact. The same is true for a chemical reaction, right? They have to collide. And so when they collide, it's not enough just to collide, right? Just like when you hit a baseball, not every time you make contact with the ball doesn't result in a home run. The same thing is true of reactants, right? They have to collide, but it's not enough just to collide, right? That collision has to meet certain conditions in order for that bond breaking and bond making process to occur. So that collision has to have enough energy, something that we call the activation energy, or E sub A, to start that bond breaking and bond making process. And it also has to occur in the right orientation to support the bond breaking and bond making process. So let's take a look at each one of those conditions separately. Okay, so let's take a look at that energy piece first. So same reaction, A2 plus B2 goes to 2AB. If I have, thinking about energy and how energy is involved, right? If I want to break a bond in chemistry, so thinking about the energy requirements, right? If I'm going to break a bond, I always, and there's no exception to this. There are very few times in chemistry when I can tell you always and no exceptions and not be lying to you, and this is one of them. If I'm going to break a bond, I have to put energy in to the system in order to break the bond. So I have to do something to put energy into the system in order for that bond to break, because otherwise the bond wouldn't form in the first place. Remember, bonds form because they're in a lower energy state when they're bonded together than they are when they're separate. So in order to separate it, in order to break that interaction, I have to put energy into the system. Always, no matter what. And conversely, if I'm making a bond, that always, no matter what, releases energy. Always, no matter what. Because again, the bond wouldn't form unless it was at a lower energy bonded together than it is when they are separated. So if I'm thinking about this in terms of the collisions, I have to, in order to start that bond breaking process, there has to be an input of energy. And that input of energy comes from the collision of the molecule A with molecule of A2 plus with B2, right? So if that A2 plus B2 collision happens when those molecules are moving too slowly, or they just kind of glance off of each other, or think about it like you don't make full contact and like you hit it, like it just doesn't go far, thinking about baseball, right? Then it's not going to be a successful collision because that bond breaking process won't start. Okay, now it's important for us to keep in mind that over the course of the reaction, it's not that those two processes are happening distinctly. They're happening simultaneously. So bond breaking and bond making are happening at the same time, but it still requires that input of energy to begin the process. So that input of energy to begin the collision process is something that we call the activation energy. And the activation energy is going to be the energy that is required to start the bond breaking making process. And it's called the E sub A, and that's going to come back later. And that activation energy is unique for every reaction. Every reaction has its own specific activation energy, and the collision has to occur with at least that amount of energy. Otherwise, nothing happens. They bounce off each other and continue as A2 and B2. So orientation. Remember how I said before that the bond breaking and bond making process don't happen separately. It's not like all the bonds break and then they make. Bond breaking and bond making is happening simultaneously. So in order for that to happen, we need to think about the orientation of the collision, right? So let's say that I have A2 and B2, and they collide this way, right? So remember that I have to break this bond and this bond, and I have to make that bond and then a bond between those guys over there. All right, so in this orientation where they're colliding side on like that, this isn't going to result in a reaction because there's not, it's like this A and this B aren't in contact with each other. So I'm going to make a bond maybe, but I'm breaking more than I'm making, and energetically it's not going to work, right? Whereas if I have A2 and B2 collide head on this way, where I have they collide in this orientation, right here, I can now make bonds between the A's and the B's, and it makes it easier to break these bonds between the B and the A. So that one absolutely will result in a reaction, right? So the orientation has to be in the right orientation to allow that bond breaking and bond making to occur. If it's not that right orientation, so if it occurs in an orientation where the things that need to form bonds aren't running into each other, it's not going to happen, right? And it's going to be a non-productive collision. Okay. So a couple of things that I want you to keep in mind as we're going through this, right? If a collision has to have enough energy and it has to be in the right orientation, not every collision that occurs between reactant particles is going to result in a reaction, or is not going to be what we call productive. Productive just means that it results in a reaction. A very tiny fraction of the total collisions between reactant particles are actually going to result in a reaction. Most are just going to bounce off of each other, okay? But I can affect that, right? I can affect the total, like how many collisions are occurring. I can make collisions happen more often, so there's more collisions. And like I can do things like heat it up to introduce more energy into the system to make a collision more likely to be productive. So I can change the reaction conditions, like how much stuff I have, the temperature, etc., to change the number of productive collisions over time, which is, by the way, how fast the chemical reaction occurs, or the rate of the reaction. But typically, even if I do that, the total number of collisions that result in a reaction is only a very tiny, small fraction of the total collisions that occur between reactant molecules. And that's something that's important. That's something that it's important to keep in mind. Okay, so in thinking about chemical reactions, I'm hoping you're getting the idea that all chemical reactions involve some sort of change in energy, right? There's energy that is required to be inputted when bonds are broken, energy is released when bonds are made, and so there's an overall change in energy. Either energy is added into the system or to the reaction, or energy is taken away, but we need a way to kind of just track those energy changes over the course of a reaction. And we do that using something called a reaction coordinate diagram, which is shown below, right? So we're gonna add some labels to our reaction coordinate diagram to kind of tell us something about how energy changes over the course of the reaction. So if we're looking at energy, the label on our y-axis, this is energy. And we're going from low energy up to high energy. So we're going in order of increasing energy. And the x-axis is going to be what we're going to call this reaction progress. which is essentially like as the reaction proceeds from reactants to products. This is how energy is changing. I want you to note that this is not, it is not time. This reaction coordinate diagram could be drawing a reaction coordinate diagram for a reaction that occurs over seconds or for a reaction that occurs over millions of years. They're all going to look the same because this isn't time. It's the progress of the reaction. It's moving from reactants to products, however long that takes. So there's no time indicated in this reaction coordinate diagram. Something I want you to consider and keep your eyes on. So what is this diagram showing me? Right, so we have two different reaction coordinate diagrams here where our axis is still going to be increasing energy on the y and reaction progress on the bottom, on the x. All right. Okay, so let's do some labeling to look at what exactly this is showing us. So if this is looking at over the course of the reaction, right, there's something in here that's showing us about the reactants, which is going to be here, what I'm going to label as A. So A is the energy of the reactants. So how much energy the reactants contain, thinking about this as being bonds, as movement of molecules, as all of these things. There's a whole bunch of different things that we're incorporating into that term, but where that is, that's going to be like the reactants, where the reactants are starting. Okay, so we have where the reactants are starting. I'm going to label this as B is going to be the products, right? So this is the energy of the products. So where it ends up. So I start at A, I end up at B, and the path that I take to get from A to B is what's shown here in black, all right? So notice on both of these that there is this kind of hill that I'm drawing out here, that I'm drawing a line to. And this energy that I'm drawing this arrow to, that's that activation energy term that we were talking about. That's the amount of energy that's required to get the reaction to go, so to start that bond breaking and bond making process. Right, and that's here too, that's that activation energy. Okay, you might be asking yourself, what is this thing that's at the top of the hill? So remember we were talking about this idea that this reaction, bond breaking and bond making aren't distinct processes, that they're happening together. So at the top of this hill, and what I'm going to label here in green as C, is forming what's called the transition state. And we'll talk more about that in class tomorrow, next time we meet. But the transition state is basically the in-between. So like bonds are in the process of being broken and bonds are in the process of being made. That's what the transition state is. Transition state is going to be the highest energy because you have bonds that aren't quite broken and bonds that are like, you have partial bonds. It's kind of really weird, all crazy. We'll talk about what that looks like tomorrow in class again, but know that it's there. Know that there's that in-between transition as we get from A to B, and it's represented at the top of our diagram. And then if I look at the difference between A to B, which I'm going to draw here in yellow, this here going to be the energy of the reaction, right? So the blue is the energy, is the activation energy, and what's in yellow is the energy of the reaction. Now notice that it's totally possible for me to have products that have lower energy than my reactants, and it's also totally possible for me to have products that have higher energy than the reactants. Both of those things are true and both of those are fine, right? So in the process from A to B, right, A collides with B, A reacts, and the reactants react, form that in-between transition state, form B, like there's some amount of energy input that's required, which is the activation energy, and then the energy of the reaction is the energy that I get outside, okay? Okay, so we're gonna talk more about this in class next time we meet, but then I would love for you to consider this question, right? So I have a reaction coordinate diagram that's shown below for my reaction, A2 plus B2 goes to 2AB. So I want you to, on your paper, in your notes right now, I want you to redraw this diagram and I want you to label it with the parts that we talked about before. So with the energy of the reactants and the products, right? I want you to label it with the activation energy. I want you to label it with the energy of the reaction, and I want you to show me where the transition state is, okay? And then let's say that I'm doing this reaction in a beaker. So A2 is reacting with B2 in a beaker, and I'm holding the outside with my hands. I want to know what am I gonna feel as I'm feeling the outside, right? Is it gonna, like, what's gonna happen? Am I gonna feel it get hotter? Am I gonna feel it get colder? Okay, think about it. Write down your answer, write down your thoughts, and bring it with you to class next time we meet. Thanks, guys.